So the goal is we're going to do today the first half of section 2.5. The part about decimal expansions, I think you should read in the book. It's not really going to come up in the rest of the course, so I'm not going to cover it today. Okay. I am going to do things a little bit differently than the book. Usually I try and stick really close to the book, but not in this section. So I'm also going to give you my lecture notes. This isn't going to happen often, but I'll put my lecture notes for this lecture up on the website. The reason I don't share them more often is that my lecture notes are rarely comprehensible to another person, but in this case I made them comprehensible to another person to help. Okay, so intervals. Okay, I believe this is almost all review. If it's not review, it's really simple. We've got real numbers. For real numbers a less than b, we define the following sets. That interval with the parentheses, that's the set of real numbers x that are strictly between a and b. Okay? We're used to calling that the open interval, right? And then the closed interval between a and b. Okay, we allow x to equal a or b in this case. And then we get the things we're used to calling the half-open intervals. So get that guy and that guy. Okay. Those are our four bounded intervals that we're used to. Each of these has a quantity we're going to call length. And the length is just b minus a. That's just the length of the real line that it's taking up, right? And it doesn't matter if you have the endpoints or not. You got the same length. Okay. Now, speaking of endpoints, each of these has endpoints a and b. Okay, so the endpoint term is the term that you're used to, that you learned when you learned intervals years ago, right? What I want to point out today is the endpoints are the infimum and the supremum of the interval. Okay, so we're going to say for us the endpoints of an interval are the infimum and supremum. Okay. Any questions so far? I hope you can look at those four intervals. Clearly the infimums are all a and the supremums are all b. So the endpoints they've all got endpoints a and b. Okay. This is with a less than b. What happens if we take these and we make a equal to b? What do we get? Well, not much, but it is important. So if we allow, well, we will allow, so we also allow a equals b Okay, what else do we get there? We get the closed interval from A to A. If we just go up to the back up to the definition of the closed interval from A to B, we replace that B with an A. Oops, circled the wrong one. We replace that B with an A. We would just get the set consisting of A, right? So that's what this is. And what's the open interval from A to A? Now we replace, yes, the empty set. There's nothing that can satisfy this condition with B replaced by A. There's no X that's greater than A and less than A at the same time. So that's the empty set, but also these half-open things are the empty set too. Okay. So those are intervals too. A singleton is always an interval, and the empty set is always an interval. Okay. Now, I'll let you think about this. We could allow A to be greater than B. But if we allowed A to be greater than B, you can check, we'll just get more copies of the empty set. So there's no point. Right? Okay. Before we leave the A equals B, let me point out that the singleton A has a single endpoint. It's A. But its length is 0. Okay? The empty set has no endpoints. Remember, the empty set doesn't have an infimum or a supremum. And of course, the empty set also has length 0. Now,
so is our definition of the length the difference between the supremum and infimum?
Yes, yes, with a caveat. Nope.
Because the empty set doesn't have.
Oh, okay. This is unfortunate. My computer is not working for me here. Thank you. Okay, thank you for reminding me of that. The recording is now restarted. So if you're watching the recording, we have these infinite intervals. They all have a single endpoint, and they have infinite length. Okay. Let me just emphasize that when we're using infinities here, those are not numbers. Those are just symbols, okay? They're just standing for the idea of let X go off forever, okay? But they're not numbers. And again, so like you take the supremum of that set, it doesn't have it. It doesn't have the supremum. It just has the infimum A. And that's why its only endpoint is A. Okay? Now there's one more type of interval. And that's if we go from minus infinity to infinity. That's the entire real line. It has no endpoints and infinite length. Okay. So now let's just, we had 1, 2, 3, 4 types of intervals. These guys in here were all those type, the previous types of intervals, but we set the endpoints equal. And then we had 5, 6, 7, 8, and 9. So we have 9 types of intervals. Okay, depending on open or closed on each side, and infinity or minus infinity. Okay, 9 types. Okay. Our plan is to prove a few theorems today. Our first theorem is going to characterize the intervals. So we have these 9 types of intervals. We want to prove a theorem that kind of doesn't look at how a set is defined. It says, but it says something is an interval. So what makes intervals special? And that's what this definition is going to try and capture. Okay. So right now an interval is just any of those 9 things we've defined. Now we're going to say that a set satisfies the betweenness property okay, if whenever you take 2 points in the set, then every point in between them is also in the set. And the way I'm going to write that is whenever we have x less than or equal to y less than or equal to z, for x and z in our set, then y also has to be in our set. Okay, so if you get a set that satisfies the betweenness property and it contains x and z, then you can take any of these points in between, call it y, it's got to be in the set. Okay. Now, I hope we can all agree that the 9 types of intervals we've defined above all satisfy the betweenness property. What I'd like to prove now is that any set that satisfies the betweenness property is one of those 9 types of intervals. Okay? That is our first theorem for today. I'm going to keep the betweenness property for as long as we can. So, we've got a subset of the real numbers. I'm going to say it's an interval if and only if, and again, when I say interval, I mean one of the 9 types we defined at the beginning of the lecture. If and only if it satisfies the betweenness property. Okay. Okay, now I just kind of bullied you into accepting that those 9 types of intervals satisfy the betweenness property. You might want to think to yourself, why does the singleton satisfy it? Well, if you're looking at a singleton set that just contains A, then your only choices for x and z would be A itself, and therefore your only choice for y would also be A, and that's already in the singleton set. So the singleton set satisfies the betweenness property. And next you might want to think about the empty set. If your set is the empty set, then there are no x and z in there. So you will never have that condition. You will never have x less than or equal to y less than or equal to z for x and z in the empty set. And therefore, the empty set satisfies the betweenness property vacuously. Okay? So, in the proof, I'm going to jump to the hard direction, and that's showing that the betweenness property implies you're one of those 9 types. Okay, so we're going to prove the harder direction. We've already proved or talked about proving the other direction. Okay, suppose we do have a set of real numbers that satisfies the betweenness property. And now we're going to make the following definition. Okay, I'm going to define a set S and then superscript O, almost like the degree symbol. The reason I'm calling it this is foreshadowing for a long time from now. I think it's in chapter 11 we're going to use this notation again. Okay, but we might as well use it now. I want this set to contain all the real numbers x such that x is neither an upper nor a lower bound of S. Okay. I'll admit that's not the most obvious definition. Okay. What I'm trying to capture is kind of the middle of the interval. Okay, the stuff in the middle, it's not an upper bound in the interval because there's things to the right of it. It's not a lower bound because there's stuff to the left of it. Okay, so this is the middle of the interval. And we're going to prove 2 things about this set. Claim 1. It's a subset of S. Okay. Well, most proofs of subsets are pretty simple. We're going to take a point in S naught and show it's in S. So, let's take an S in S naught. Okay. The rule with S is it's not an upper bound and it's not a lower bound. That means there have to be elements of S, of big S, on both sides of it. So by the definition of SO, there are X and Z in S with X less than S less than Z. Okay, that's because it's not an upper bound and it's not a lower bound. Well, those things are both in S, and S satisfies the betweenness property. So little s has to be in S as well. That's the proof of the claim. Okay. Any questions? Now, I called this claim 1. I realized we're not going to do claim 2. We're going to jump straight to the finish here. So to finish the proof, we consider cases. And I'm just going to talk through a couple of the cases. They're all very similar. Okay. What if S is bounded? Okay. Remember, our definition of bounded means bounded on both sides. So it's got an infimum and a supremum. Okay? The infimum and the supremum are not in SO. Okay? But anything between them is in SO. And that's because anything between them, it can't be a lower bound because it's bigger than the infimum, and it can't be an upper bound because it's smaller than the supremum. So what do we have? SO, well, here I want to write this a little bit differently. SO we just talked through this. It's the open interval from the infimum of S to the supremum of S. Because any point in there, it's not a lower bound and it's not an upper bound. But also, and I wrote my O in the wrong place there, move it to the right place. Our claim said that SO is contained in S. Okay. Now S is bounded. The absolute largest set that S could be would be the closed interval from its infimum to its supremum. Okay. That's because no set contains anything smaller than its infimum or larger than its supremum. Right? Now, there are 4 possibilities for S at this point. Right? It either contains its infimum or it doesn't, or it contains its supremum or it doesn't. But because it has to contain the open interval between the infimum and the supremum, those are the only 4 choices. And all 4 of those are types of intervals that we defined above. Okay. Let me give you a taste of one of the infinite cases if S is bounded only below. Then okay, what's SO? S has an infimum, so anything bigger than the infimum is not going to be a lower bound. And S, it's bounded only below, so it has no upper bounds. So the set of things that are not bounds for S is the open interval from the infimum to infinity. Now that's contained in S by our claim. And the absolute largest that S could be is the half I'm sorry, the closed interval from its infimum to infinity. Okay. Well, there's two choices for S. It either contains its infimum or it doesn't. Okay. Either way, it's one of those 9 types of intervals that we defined. Okay. Are there any questions on this? If S is bounded only above, that would be case 3. It's exactly the same, but with supremum instead of infimum. And if S is not bounded on either side, that case 4 is really, really easy. S isn't bounded on either side, so SO is all real numbers because no real number is a bound for S. And then that forces S to be all real numbers. Okay. That's the end of the proof. Questions?
So how exactly are we showing that SO is an interval? Is that sort of just like an obvious claim?
Mm-hmm. So let me go back up. You're asking basically, how am I getting that part? Right. Okay, so at that point we know S has an infimum and a supremum. Okay? Take any point in between them. Okay? And now think about the definitions of infimum and supremum. A point in between them would be greater than the infimum. That means that it isn't a lower bound. And it's less than the supremum. That means that it's not an upper bound. So it's.
And we use the betweenness to get the less than or equal to.
No. So we already used betweenness in the proof of the claim. Mm-hmm. Up here. That's the only place we use it.
Wouldn't we have to use it just because everything is between the infimum and supremum doesn't mean that there isn't necessarily gaps, but the betweenness guarantees that there aren't gaps, right?
Actually, not. The definition of SO is what I'm getting this from.
Okay, since it's kind of like a complement. It's like it's getting everything inside. Okay, I see now.
Right. So I'm saying, I'm saying anything between infimum and supremum is not an upper or a lower bound of S. So it is an SO by the definition of SO.
Okay, I see now.
And then the claim says SO is a subset of S. And then just the definition of infimum and supremum mean S has to be contained in the closed interval from infimum to supremum. Okay.
Professor, can I ask a question?
Of course.
So, if I understand it, we didn't prove that if it has an interval, then it satisfies the betweenness property. We assume that it satisfied the betweenness property. Wound up with these 4 cases, because in any of these 4 cases, you get some sort of, you can represent the set in some sort of interval notation.
Yes.
Okay.
Yeah, and we skipped the easier direction, which is you take any of those 9 types of intervals and you show they satisfy the betweenness property.
Right. And just one final clarification.
Mm-hmm.
We do have this property that any set of real numbers is either bounded, bounded only above, bounded only below, or not bounded. So that covers all sets of reals.
Right. Yeah.
Okay.
Yeah, in both directions, you're either bounded or not bounded.
So maybe this is a stupid question, but
Go
we're
ahead.
trying to show that if S satisfies the betweenness property, then we can write S as an interval.
Yes.
So here we've shown that S is a subset of the interval.
I'm sorry. What I didn't write the full argument because I'm trying to. I was trying to conserve time. So S is one of. Let me look at case 1, okay? We know that S contains the open interval from the infimum to the supremum, and it's contained in the closed interval. So that's the smallest it could be. It could contain the infimum but not the supremum. It could contain the supremum but not the infimum. Or it could contain both.
Okay, and that just follows from S being a superset of this open interval or a subset of this closed interval.
Yeah, there's only 2 points that doesn't tell us about, and it's the infimum and the supremum.
Cool, thanks.
Yeah. Okay. Next, definitions that you know, but I'm going to define them differently, okay? So you're used to calling these intervals open, closed, half open, right? Let's define those using our new terminology, I guess. So an interval is open if it contains none of its endpoints. It is closed if it contains all of them. And then there's the half open. Or if you like, you can call this half closed. Here the definition is a little bit weird. To be half open or half closed, you have to have 2 endpoints. Not every interval has 2 endpoints, but you have to have 2 endpoints, and you contain precisely one of them. Okay. So my intention here, these are different definitions of terms that you already know, and these definitions agree with the terms that you already know. Okay. Let's look at some examples.
So what do we call the ones that have infinity?
We follow these definitions. So we're going to get to that. We're going to go through all 9. Okay? I'm going to assume that A is less than B, strictly less than B. And then let's just work through what these are. The open interval, we call it the open interval from A to B. It's open, thank God, right? Because it has endpoints A and B and it doesn't contain either of them. Okay? the closed interval from A to B is closed. Again, thank God, and the two others, the half opens, they're exactly as you learned them, or I guess I should say our definition agrees with what you learned. Okay, now the infinite ones. If we go from A to infinity, not including A, or we go from minus infinity to A, not including A, are they open or closed?
Open.
Open. Each has one endpoint and it doesn't contain it. Closed intervals. Well, I gave away the answer there. These two are closed. They each have one endpoint and they contain it. Okay, now we've got three weirdo intervals. What about the singletons? What is a singleton? Mm-hmm. It has one endpoint and it contains that point. Okay. Now we get a little bit weirder. The empty set, is that open or closed? I should let you vote on it.
I'd say neither.
Yeah, I see. We can do polls in Zoom. If we had time to burn, we would totally take a poll. We'll follow the definitions. Ask yourself, is the empty set open?
Yes.
Yes. Right? It doesn't contain anything, so it certainly doesn't contain its endpoints, whatever they would be, Now, is the empty set closed?
Yeah.
Yes. It has no endpoints, and so it contains all of its endpoints. Right? The only thing it isn't is half open. It's not half open. So the empty set is both open and closed. I'll put an exclamation point for that. Okay, and these are not mutually exclusive. Final interval. All real numbers. That is both. That is also both open and closed. Okay?
Excuse me, but how do we know if the empty set is open and closed if it doesn't seem to have any endpoints?
We're just following the definitions.
Okay.
Right? We made those definitions, and now we're saying, okay, according to those definitions, it's open and it's closed. Same with the real numbers. The real numbers have no endpoints, so the real numbers contain no endpoints. That makes them open. But also, the real numbers have no endpoints, so they contain all of their endpoints. So the interval consisting of the real numbers contains all of its endpoints, so it is closed. Okay? Now, don't freak out too much. Only the empty set and the set of all real numbers. The empty set and the set of all real numbers are the only sets you're going to see in this semester that do this, that are both open and closed. Okay? In the second semester, we're going to see all kinds of sets that are both open and closed. But You don't see that in the real numbers. In the real numbers, it's just the empty set and the set of all real numbers. Second semester, we're going to leave the real numbers, and this is going to happen all over the place. Okay. Now, I realize I have 1 minute left. So let me pause the recording.